Okay, in this video, let's go through problem number 13 in assignment 3. So in part A, you're given the equation r equals 4 plus 3 cosine theta, or in your case, your numbers will most likely be different, but something of that form. And we want to find the area of this associated region. The first thing to notice is that if you replace theta by negative theta, our equation is unchanged, right? 4 plus cosine of negative theta is the same thing as 4 plus 3 cosine of theta. That's because theta eats negative signs, because it's an even function. And so that implies that you have symmetry about the x-axis. So we can just confine our attention to the top part of this region, find its area, and then double it. So essentially what we would need to do is we need to know when we start out at this point here and when we get to this point right here. Right? We want to think that if theta is time, it traces out this portion of the limacon with time, and we want to know at what times does it do that. So in order to understand how that works, we look at the equation r equals 4 plus 3 cosine theta, and we kind of graph it in as if r and theta were Cartesian coordinates, right? So basically what you're doing is you'd be graphing 3 cosine theta, which is just a stretched out cosine, and then you'd be shifting up everything 4 units. So it should make sense that this is the resulting picture. The biggest it can be is now going to be 7. The smallest it can be is 1. And then we'd have a picture that looked like that. Okay. So this would be pi, this would be 2 pi. So what's happening is the red portion that I've highlighted corresponds to this portion of 4 plus 3 cosine theta. So that tells us, right? So that top portion of this limacon is starting when theta equals 0, and it stops when theta equals pi. So then it's not too difficult to actually find the area. We would say, well, we go from 0 to pi. We need bounds on r. So if we take, for any angle between 0 and pi, if we take some ray at that angle, we see that the inner boundary is 0 and the outer boundary is 4 plus 3 cosine theta. And we would have 1 r dr d theta. Now when we integrate the when we look at the inner integral, we're going to get r squared over 2 from 0 to 4 plus 3 cosine theta. Plugging all that in, we would get 1/2 4 plus 3 cosine theta squared. So let's kind of write out what that would be. 4 squared would be 16, 3 cosine theta squared would be 9 cosine squared. Then we would have the cross terms, the outside term and the inside term, and the FOIL. So that would give us 12 cosine theta, but we'd have 2 of those, so 24 cosine theta. And all this would be, of course, integrated from 0 to pi. Oops, sorry. Not quite yet. We have to integrate it with respect to d theta first before we can do that. So we get 16 theta. The key right here is to rewrite cosine squared as 1 plus cosine 2 theta over 2. Right, that's the half angle formula. And so when we integrate that, we're going to be integrating 1. That would give us a theta. And we'd be integrating cosine of 2 theta, which would give us sine of 2 theta over 2. And then the integral of 24 cosine theta would just be 24 sine theta. Now we can go from 0 to pi. Okay. Plugging in pi and 0, so this would give us 16. This would give us pi minus 0. This would give us pi minus 0. Plugging in pi would get this, minus plugging in 0, which would be sine of 0. Plus 24 sine of pi minus sine of 0. Okay, so what does all this amount to? You get 16 pi plus 9 halves pi plus 1 half. Well, what's sine of 2 pi? It's 0. And what's sine of 0? Also 0. So this would just be 1 half times 0. Plus 24 times sine of pi is what? Well, again, it's 0. So 0 minus 0. So we would get 16 over 2, which would be 8 pi, plus 9 fourths pi. So putting everything over 4 and pulling a pi outside, you would get 32 plus 9, which is 41 fourths pi. Okay, but that is just the top of my region, right? That is just this portion here. So I need to multiply by 2, and so the area for part A would actually be 41 over 2 pi. Okay. Now what about part B? Now we're supposed to find the area of the region outside the inner loop and inside the outer loop of the limacon, now given by, for my numbers, 3 plus 6 cosine theta. Okay, so probably the easiest way to do this is actually first think about part C, which is the area of the loop. Right, so this is the part that I did in class. Right, so let's think of how that worked. So the idea is we need to think about what 3 plus 6 cosine theta looks like when we graph r and theta as if they were Cartesian coordinates. So remember the picture I had was something like this. Right, so at the very top it was 9, at the very bottom, we had -3. Here was 3. So here, right here, that's 2 pi. Here is pi. This point is pi over 2. That point is 3 pi over 2. And we also found it useful to know where this was equal to 0, right? So 3 plus 6 cosine theta was equal to 0. That meant cosine theta was equal to -3/6, which was -1/2. This happens at 2 pi over 3 and 4 pi over 3. So we have 2 pi over 3 right here, and 4 pi over 3. Okay. So using all that information, we found out that going back to ordinary Cartesian coordinates now, we found that the loop gets traced out as you go from 2 pi over 3 to 4 pi over 3. Namely, it corresponds, so this portion of the graph right here, it's in red, corresponds to the loop, and it's traced out in that kind of direction, right? So here we have theta is 2 pi over 3, and here we have 4 pi over 3. Okay, so to find the area of that, we just need to let theta vary from 2 pi over 3 to 4 pi over 3. Now, for an angle in that range, we just take a ray from the origin and see what happens. So the first region that it encounters, or the inner boundary, would be 0, and the outer boundary would be actually given by the limacon itself, which is 3 plus 6 cosine theta. And we would have 1 r dr d theta, because we're trying to find area. Right, so this would be the area for the inner loop. So we're really answering part C at the moment. So it's going to be a very similar type of similar type of calculation to what we did. Namely, we integrate with respect to r, we get r squared over 2 from 0 to 3 plus 6 cosine theta. So we'll have 1/2 3 plus 6 cosine theta, quantity squared. We square all that out, so we get 9. 6 cosine theta squared would be 36 cosine squared theta. And if we look at the cross terms, we'd have 3 times 6 cosine theta, and we'd have 2 of those, so that would actually give us 36 cosine theta. So we have to integrate that from 2 pi over 3 to 4 pi over 3. Now again, we need to write cosine squared of theta using the half angle formula, so that's 1 plus cosine of 2 theta over 2 plus 36 cosine theta d theta. Okay, so let's go ahead and integrate this with respect to theta. So we'd get 9 theta. We'd have a 36 over 2, which is 18, and that integrates to 18 theta. There'd be a 36 over 2 times cosine of 2 theta, so that would be 18. The antiderivative of cosine would be sine, but because it's 2 theta, we'd actually get another 2 in the denominator. And then the antiderivative of 36 cosine theta would be 36 sine theta. And that would all be from 2 pi over 3 to 4 pi over 3. Okay. So this is 27 theta plus 9 sine of 2 theta plus 36 sine of theta, all from 2 pi over 3 to 4 pi over 3. It's kind of messy, but let's just go through it. So we're going to get 27, so we're going to get 4, we can put 4 pi over 3 minus 2 pi over 3. And now we're going to get sine of, well, we're going to take 4 pi over 3 and stick it in for theta, so that's going to be 2 times 4 pi over 3, or actually 8 pi over 3 minus sine of 2 times 2 pi over 3, which is 4 pi over 3. And plus 36 sine of 4 pi over 3 minus sine of 2 pi over 3. Okay, so a lot of stuff to evaluate. Okay, 4 pi over 3 minus 2 pi over 3 is 2 pi over 3. What's sine of 8 pi over 3? Well, you can look it up, but it's the same thing as sine as 2 pi over 3, and that's radical 3 over 2. Sine of 4 pi over 3 turns out to be negative radical 3 over 2. Sine of 4 pi over 3 is again the minus radical 3 over 2. And as I said, the sine of 2 pi over 3 is radical 3 over 2. Okay. Simplifying a little bit here, so 27 times 2 pi over 3. The 27 over 3 is really 9. And 9 times 2 is 18, so we have an 18 pi there. This would be the radical 3 over 2 minus negative radical 3 over 2. The minus minus becomes plus, so we get really 2 radical 3's over 2, which is just radical 3. And the same kind of logic leads us to, this will be minus 36 radical 3. And so we'd get 18 pi. So the two terms, 9 radical 3 and minus 36 radical 3, can be simplified to give minus 27 radical 3. And if we want, we can pull a 9 out of both terms to get 9 halves 2 pi minus 3 radical 3. Okay, so that is the solution to the inner area of the inner loop. And now once we know that, what we can do, so this was the area of inner loop. So now what we want to do is return to part B. So we want to find the area basically of the limacon that is outside the inner loop. Right? So it says outside the inner loop and inside the outer loop. So going back to our picture here, my kind of crude picture. Now what we want to find is basically all this stuff in here. So now it should be kind of clear how we could do that. Namely, what we could do is just find the area of everything, namely everything in here, including the inner loop. And then since we know the area of the inner loop, we could subtract it off, and that would give us the area of the red shaded region. So again, this figure is symmetric, so if we want to find out the area of the entire thing, everything shaded, including the inner loop, we could just focus on the top portion, the portion that's above the x-axis, because again, this figure is symmetric. So what we need to do then is to know, well, if we start right here, we want to trace it until we get to this point. Now it's tempting to think that that is 0 to pi, but remember, it's not. If we go back up to our picture here, it's too far, it's not the right one. There we go. Remember, that top portion here, that was only, well actually let me make it in blue, so stick with me here. All this stuff from here to here, that corresponded to this on the graph. Namely, it corresponded in everything from theta to 2 pi over 3, right? That's where it stopped. Once you went past 2 pi over 3 is when you started going and doing part of the inner loop. So it's not from 0 to pi, it's from 0 to 2 pi over 3. So namely, the idea is that long as theta is between 0 and 2 pi over 3, the area that you, well, the region that you get will look like that. And that's what we want, right? Because that's what we're going to do, is take that shaded area. So we're going to go from 0 to 2 pi over 3. And well, as long as theta is between those two values, if you take a typical ray, its inner boundary is going to be 0, and the outer boundary is going to be, again, the limacon, 3 plus 6 cosine theta. 1 r dr d theta. Now, we can save ourselves a little bit of work, right, because this looks exactly like what we did a little bit ago, except the theta bounds are slightly different, right? The inner integral in terms of r is exactly the same as what we did right here, right? So this 1/2 27 theta plus 9 sine 2 theta 36 sine theta, right? That where did that come from? Well, that came from, well, we integrated the inner thing that was r, so it became r squared over 2 when we plugged in r 3 plus 6 cosine theta, and we squared it out, and we simplified and integrated with respect to theta. So all that stuff is exactly the same. We just want to change the bounds to be slightly different. Okay, so namely we want 1/2, let's see, I don't even remember what it was. So we had 27 theta plus 9 sine of 2 theta plus 36 sine of theta from 0 to 2 pi over 3. So let's check if that is indeed correct. Yes. Okay. That's what we want to do. Oh, whoops, and this was 27 theta. Okay. So we plug things in now. Notice that when we plug in 0, the first term we would get 0, the second term sine of 0 is 0, and the same thing for the last term. So when we plug in 0, everything goes away, so we only really have to worry about plugging in 2 pi over 3. So we plug in 2 pi over 3. This would be sine now of 4 pi over 3, and this would be 36 sine of 2 pi over 3. So again, 27 times 2 pi over 3, what happens? 27 over 3 is really 9, so we get 18 pi. This would be 9 times, well, sine of 4 pi over 3, remember that was negative radical 3 over 2. And sine of 2 pi over 3 was radical 3 over 2. So this would give us 9 pi. We'd have minus 4 in the denominator. We'd have 9 radical 3 plus, again, 4 in the bottom, 36 radical 3. We could simplify that to 9 pi. So we'd have 36 radical 3 minus 9 radical 3, so this would be 27 radical 3. And we can't really simplify that anymore. Okay, but that's the area. Now we need to double it, right? Remember, that was just the area of the top piece. Right, that was the area right here of all this stuff. So we need to double it. So we really get 18 pi plus 27 radical 3 over 2. Okay, so finally, to find the area of the region outside the inner loop and inside the outer loop, we have to take this answer. So now we're finally getting the answer to part B. We have to take this, and we have to subtract the area of the inner loop. So let's go back and see what that was. So this was 9/2 2 pi minus 3 radical 3. So 9/2 2 pi minus 3 radical 3. And let's see what we can do with this. So we'd have 18 pi plus 27 radical 3 over 2. We could simplify this to just 9 pi. And this would become plus 27 halves radical 3. Right? So 18 pi minus 9 pi would become 9 pi. and we'd have 27 radical 3 over 2 plus 27 radical 3 over 2, which would just give us 27 radical 3. Okay, and that would be our answer then for part B.